Hello everybody and welcome to this new video tutorial about the texture editor of scenProc. In this video tutorial I want to talk about two new features that have been added recently to the texture editor, and that is the use of object-based classification instead of pixel-based classification, and the use of machine learning algorithms to find detect the right features. So I'll cover each of these in this tutorial. Um, But let's get started. I've loaded here a sample image with some vegetation, some grass, some houses, and the task I want to achieve with this texture filter is that I want to detect the trees in this image so that I can create scenery for them. The traditional approach to do that before these new features might be to calculate the normalized difference vegetation index, the NDVI, and then apply a certain thresholding to the output and select the areas that are above a specific threshold. So let's have a quick look at that. So we have our image here, which is a 4-band image. So it has a red, green, blue, and a near infrared band. With that information, I can calculate the vegetation index, which you see here. And then I can say, let's say everything above 160 or so, I consider to be vegetation. And you probably already see it. The trees are detected quite well, but we also have quite a lot of other elements being detected, like grass or fields. So why is that? When we use this kind of approach, the texture filter is basically looking at each pixel individually. And by looking at the color values or the vegetation index in this case of that pixel, trying to decide if it meets the thresholds that you specify here. And if we as a human look at this image, we can rather easily see that this is a field and this is a vegetation, is a tree. But if I would zoom in a lot and sort of look at individual pixels, also for you as a human, it becomes much harder because this green pixel, is that tree or is it grass? And this green pixel, is it tree or grass? They look quite similar. So that's why with pixel-based classification, it can sometimes be hard. And that's also why in the scientific literature it is found that object-based classification usually gives better results. So until now, it was not possible to do the object-based classification, but in the latest version of scenProc, you can do it. So I first want to talk about how you can segment the image into different objects, and later on we will then discuss more how we can use those objects. So the idea of object-based classification is that you first segment your image, well, this is an image of maybe 1000 by 1000 pixels, so it has maybe a million pixels, that we want to segment them into a number of objects that's, yeah, at least, so we don't have to consider a million individual pixels, but we can look at groups of them. scenProc has two steps now to do this object segmentation. The first one is the k-mean clustering approach, which is an algorithm that basically you tell it how many clusters you want, and then it tries to divide the input into that number of groups, looking at the mean value of the groups to separate things. One important thing to remember is that this uh, segmentation approach, this clustering approach, needs a one-band image as input. So I can't feed it with the 4-band image that I have here. So I will first use a brightness step in between, which is basically making a grayscale version of the image, and then I can feed that to the clustering. So we have our color image with the near infrared included. We turn that into a brightness image, and that brightness image I can cluster. And here you see with the different colors represented the different clusters. So in this case, we have specified that we want 8 clusters to be created. I can Use more or less. That's a parameter you can vary with to see what results you want. You can also specify how many attempts the algorithm will do. Basically, yeah, the more attempts you do, the more optimal the result will be, but of course at a performance cost. And the cleanup iterations attribute basically specifies how many times you want to do erode and dilute steps on the output. Because if we look at the raw output of the clustering, you can see it's a little bit noisy. There might be sort of pixels that belong to another cluster. And by running the cleanup on it, you get a more clean result. So this is basically an image where you have different objects in there for for the different segments, but it's a bit hard maybe to see what this really means. So let's go to an example of how you can use those objects. We could, for example, calculate the mean color for each object. So we feed the labels, the segments, as one input to this step, and the other input is the original color image. If you look closely, you will see that inside the dot of the connector, there's now a number, and L means that it expects object labels as input. So coming from either the k-means clustering step or the multi-resolution segmentation step that we're going to discuss next. And then we have this image where for each object, the average, the mean color values are being calculated. So if you compare that to the original image, you can see that yeah, some things are simplified already. So that's how you can use those labels to derive properties for those different objects. Besides the mean, you can also do standard deviation or minimum and maximum value within the object, but we'll come in to that in more detail later on. So this is one approach, the k-means clustering approach. But if you look closely, mainly here near the roads and those houses, you see that the output is not that optimal. Some parts of the roof are a bit blended with other areas. So that's why I also implemented a second object segmentation approach, which is the multi-resolution segmentation. So that's another new step. I'll add that as well. That step takes the color image as input again, or it takes the color image, I should say. So you don't need to go to a one-channel brightness image here. You can just feed it with a color image. And let me quickly, I'll explain later why I do this, but for performance reasons, I'm going to change one parameter. So I can then run this step, and let's just go ahead and first look at the results, and then I'll explain you the different parameters of the algorithm. So also with these labels, we're going to calculate the mean value. And then you see here we have all the objects and we can calculate the mean value again. And if you compare these two, you will see that in general the one from the multi-resolution segmentation is a better representation of the original object. So in general, I would advise you to use the multi-resolution segmentation step, but it takes more processing time to calculate the objects with that one. So if performance is a real uh, bottleneck for you, then you might want to consider the k-means clustering. So let's go to the multi-resolution segmentation step, because I just showed you the output and we haven't talked about yet what it does. I explained before that the k-means clustering basically tries to divide the pixels into the number of groups that you have specified by looking at their values. The k-means, that's the k-means clustering, sorry. The multi-resolution segmentation step uses a very different approach. It starts with each pixel of the image being a segment, and then the algorithm will go over the different segments and each time consider which merge with a neighbor segment will give the best results. So looking at a pixel, it will consider the 4 neighboring pixels next to it and see which of those pixels has the least cost to merge it with that pixel. Um, and I'll explain in a bit how that cost is calculated. And then at least cost merge is being performed as long as it's below a threshold that you can specify. So that way, it's sort of a region growing algorithm that starts to merge things together, and then the different objects in the image are being formed until the merge becomes too expensive, so it has too much influence on the resulting output, and then it's not being performed anymore. How does the algorithm work? I'll quickly jump to the manual. Because it has a simplified representation of the formulas in there. The cost factor for the merges is being calculated based on 2 factors. There's a color factor and a shape factor. And each of these there's a weight that determines if the color factor or the shape factor is more important for you. Then the color factor is being calculated by looking at each of the bands of the image, so the red, green, blue, and near infrared in this example, and calculating a band factor, which is again multiplied by a weight you can give to the band. So that's the color factor, and it basically looks at if I merge 2 pixels, how much does the color change? So is the result of the 2 merged segments, does that give a very big difference in the color compared to the 2 segments we had before? In that case, it's an indication that the pixels are maybe not really similar, so not really a good choice to merge. And if the cost is low, then well, it might be that they were both grass or were both part of the same house because they were quite similar. Then the second part of the merge cost is the shape factor, and the shape factor is once again composed of 2 different factors. There's a compactness factor and a smoothness factor. So the compactness factor looks at sort of how similar to a rectangle the resulting shape is. So if it results in very weird shapes with parts sticking out, that will give an extra cost here. And the smoothness factor also looks at how smooth the boundary of the shape is, and it prefers one that's relatively smooth and doesn't have a lot of bumps in it. And once again, with the compactness weight, you can balance how heavy those different factors are being weighted. So all those different factors that you've seen in those equations in the manual, or those weights, you see them here. So we have the color band weight, which gives the weight for each of the 4 bands. By default, each of them will have a weight of 1/4, so that they sum up to a weight of 1. But if for the feature you are detecting, you know that the color of one band is much more important, you can give that band a higher weight by changing these band weights. Then the color weight is the weight that determines if the color factor or the shape factor is more important, and the compactness weight is the one that is between the compactness and the smoothness. And by default, those 2 weights are put at 0.5, which means that color and shape are both weighted for 50%, and that in the shape factor, the smoothness and the compactness are also both weighted for 50%. But you could vary them and see if that gives a better result for your image. Then there's the maximum tile size. That's a performance parameter, because this algorithm can take quite some time to run. And you might have noticed that I quickly changed this to a lower value after I added the step to my texture filter. That's because else it might take like 10 or 20 seconds to calculate the objects in this image. And for this tutorial, I thought that would not be really nice to wait that long. So if you put this value to a lower number, like 256 means that the maximum size of a tile is 256 by 256 pixels. If your image is bigger than that, then the algorithm will process it in different tiles, different segments, and each of these tiles can be calculated in parallel using separate threads, so that speeds up the calculation quite a lot. And as you can see here, I've specified 256 pixels. The image is around 1000 pixels. So you see we have 4 tiles horizontally, and vertically we also have something like that. There's a part of the image missing at the bottom. And you can see here very clearly that there's an edge between those tiles. So in each of the tiles, the object segments have been calculated, and in the neighboring tile, it has been done separately. It might look very disturbing in this view, but if we actually look at the resulting mean object colors, if you look closely, you will see the edge, but in general, it doesn't have a lot of impact on the outcome. And then I think the additional performance gain from doing it in parallel is more important than the image quality. But if the image quality is very important for you, you can always increase the maximum tile size attribute. Then the next option is the mutually best merge. That specifies if the algorithm tries to find a mutually best merge or not. So like I explained, the algorithm checks a segment and then looks at the 4 neighboring segments and then select the one with the least cost to merge. So let's say we checked a certain segment and the segment to the left is the most optimal one to merge, with the one with the least cost. Then what the mutually best merge option does is that for that segment on the left, it will also look at its 4 neighboring segments and check if the segment on the right is also the best candidate to merge for that segment on the left. And only if sort of the merge is for both of them the most optimal solution, it will be performed. So as you can understand from that explanation, this means that there will be more calculations being done. So it has a slight performance cost again, but in general, it gives a better quality result. Then we have the number of iterations. That's the parameter that determines how many iterations the algorithm can maximum run. So that's how many times it will check each of the segments to see if there are merges that can be done. Then below that, there are 2 parameters which are actually not inputs but outputs. That's why they're gray. And they tell you how many segments have been calculated in the image. So in this case, it's just over 8,000 segments, and how many iterations were used to reach that result. So you can see here that the algorithm didn't run 100 iterations like we specified, but it only needed 14 to create this output image. And then we have 2 parameters left. One is the random seed, which is just the seed for the pseudo-random number generation that's being used to go over the different segments. To ensure that you get the same result if you run the algorithm later, the seed is stored, so you get it's a pseudo-random sequence that you get, and each time you get the same sequence, because else the result will be different each time you run the algorithm, and that's also not desirable. And then the last parameter is probably the most important when it comes to tuning this step. It's the scale parameter, and that's basically the threshold that determines what the maximum cost is in the algorithm. So if the cost of merging 2 segments is above this threshold, it will not be performed. And it basically means that the bigger you make this number, the bigger the segments are that the algorithm will create. So we had it at 100 now. If I put it at 1000, and it will start calculating it now, you will see here in the image that we get fewer segments. Well, you can also see that here. Instead of 8,000, we just have over 1,000 now, and each of them will be bigger. So if I look at the mean of color value of each of those segments, you can see the result is, it's giving bigger segments. On the other hand, if we look like closely here to those houses, those roads, you can also see that things start to be blended together now. So I think we've made the segment size a bit too big now because we're not getting segments anymore that represent one type of feature. They either represent the tree or they represent the field or the house or the road, but things are getting mixed. And if that happens, it becomes more difficult later on to classify those segments. So I think we made the segments a bit too big now, so maybe we should decrease the size a bit again. I'll put it at 200 this time. Well, the algorithm is calculating it again. And if we now look at the mean value, well, I think the different objects are being represented better. So now we have, what do we have? We have 4,600 segments in the image. So that's the first bit of the new functionality in the texture filter. You can now do object-based classification because you can segment the image into objects. But how to use that? And that's what I'm going to cover in this second bit of this tutorial. So let me clean up this filter a little bit. I'm going to remove the k-mean step because we're not going to use that. But let's say we've calculated our image. We've calculated the vegetation index. We have the color, and I want the standard deviation, which is here, standard deviation object based. So I feed the labels to the two mean steps. This one is mean, and then we want the standard deviation. So, and for now, I'll just connect these two so that the filter is valid again, then I can show you the output. So we have our color image, we have our vegetation index image, we have the object segments, and then we can calculate the average color value of each object. So that's the red, green, blue, and near infrared average value of each segment. And this is the average vegetation index of each segment. And we calculate the standard deviation of each segment. So that's the standard deviation for each color band within the image. And as you can see, the values are much lower. You see if I hover the mouse over, it's like 15 or 20. So the image looks a lot darker, but it's for each segment how much variation there is in the colors. With these three things, we will try to classify the trees. How can we do that? If we do it on the traditional approach, we would, with threshold steps and those kind of steps, try to define our own criteria for when something is vegetation or not. But that can be quite hard to find the right thresholds and the right logic to use. So a new step has been added to scenProc for that, and that's the support vector machine step, which is a machine learning step that where the machine learning algorithm tries to determine sort of what are the criteria for the feature that you want to detect. So you feed this step with the input criteria that you want to use, and you give it a number of samples as training data, and then the algorithm will learn how to select things, and we can use that for the classification. So as input, we will use the three sort of characteristics of the different objects that we have. So we have the mean color, we have the standard deviation, and we have the vegetation index. So the mean color and the standard deviation, that's a 4-band image because that's done for each of the bands in the input image. So the red, green, blue, and near infrared. And this one is just a 1-band image because it's for the vegetation index. So in total, we have 9 sort of criteria being used. And then I can connect that one to the machine learning step, and we get the output. At the moment, of course, it doesn't work yet because we haven't told the machine learning step yet what we want to detect. For that, we go to the sample point tab here, and then we can click on our image to select what we want to detect. So I'm going to put training some training data in the trees, in the tree area, because those are the features we want to detect. I do this by clicking with the left mouse button on the image. I also will tell the algorithm a few of the things that I don't want to detect. So I click in the field, I click in the grass, I click a bit on the road. Let me click on the roof as well. So sort of to help it that those are things I don't want to detect. This is normally a bit of an iterative process, as I will show. So I've now made maybe 20 or so sample points. So if I now click on the support vector machine step, it will train the algorithm with that input and then run it over the whole image to do the detection. And let me turn on the merge results. Well, you see that the vegetation has been detected quite well already, but there are some false positives over there. So what we will do is add some more sort of negative sample points, telling it those are not features we want to detect because it's got some shadow and some other things. So we added a few more points, then we just click the step again. It will retrain the algorithm. Well, you see the result gets better already. Here's also some big shadowy thing. Let's get rid of that. And with a couple of iterations, you will get results that are quite good. There might also always be like some very small areas being included that you don't want. I'll try to put a few more points, and let's put a few more positive points here as well to help the algorithm. Run it again, train it again, run it again. So we're getting quite close, I think, already. We could always do the erode and dilute steps to get rid of some of the small noise, and then, yeah, to clean up the results a bit. But this basically shows how you can use the machine learning to detect the features that you want. And it becomes relatively straightforward to just click on what do you want to detect, what do you not want to detect, and wait for the algorithm to find the best results. The algorithm, if you go to the properties tab here, has quite a few parameters that you can set again. The most important one is probably kernel type. And I just realized that this is maybe not even the best kernel to use. From the tests I've done, the RBF kernel is, in general, giving the best results. You already see that the output changed a bit. The manual explains also what the other parameters do, but they seem to have less influence on the overall result. And that way, yeah, we can now have our vegetation being detected by just providing enough samples to the algorithm. Of course, this is a very simplified example because I'm just using one image in this case on which I train the algorithm and then show you the results on the same image. If you want to do the vegetation detection for a real project, you probably have a bigger area, maybe a whole city or a whole state that you want to detect. You will, of course, not provide training data for all those images. The idea is that you provide the input for a couple of representative areas that show the different sort of variations of what you want to detect, and then you can run that trained algorithm on all the images. I'm going to load an example that shows you, do I want to continue? Yes, I don't want to save this. So this is a similar uh, filter. But instead of just the mean color, standard deviation, and the vegetation index, I'm also using the water index, the brightness, and the intensity difference. And those are all criteria that are found in scientific papers. So we have even more criteria is included here. And also I have loaded more. I'm going to lower this one a bit so that we can see the image a bit better. I have more images. So for this one, I've provided training data. This image, I haven't provided training data, so that's just to test it. For this one, I've provided training data. So this one we have training data. So we have a number of images where we provide the training data. The algorithm will then gather the data from all those input images. So the training will take longer in that case because it might have to go over 5, 6 images, collect all the sample points that you provided and use that to train the algorithm. But then you can run it on different images. And to test it, I've loaded different images that show different kinds of vegetation. And I can quickly show you the result of that as well. Um, I'll do it merged with the input image. That gives a better result. So you can see here that it gives very good results on detecting the vegetation. If I go to this next image, it's calculating now, which might take. You see, this is an image with only a few training points, only some points we don't want to detect, but still it detects the vegetation quite well. And if I go to yet another sample image, and I believe this is one without any training data, you see that it classifies the vegetation in this image very, very nicely. So by including some images that you haven't used to generate the sample points from, you can sort of verify that the algorithm is trained well enough or not. So that's the end of this video tutorial. I hope you enjoyed this explanation of the object-based classification and of the machine learning algorithm. They will be available in the development release from now on. If you have any questions about how to best use them or if you encounter any issues, of course feel free to post it on the forum. Thanks for watching and I hope you enjoy the new features.